Already looked at how we can instantiate a deep learning model. We've already looked at the input layer, and the input layer is where you set the parameter for input shape, and the input shape is the number of features you have in your data set. Then another thing we can add, as I said, was the activation function. So that's the other thing we discussed. So for today, what we are going to look at is the stochastic gradient descent. And for stochastic gradient descent, it's just a simple thing. So when we were looking at deep learning models, we saw that the weight and the bias term were random. So this line kept on changing each and every time we ran our code. So how do we fix that so that we get a fixed weight which gives us the best accuracy that the model can get? So that's where stochastic gradient descent comes in. So let me make this full screen. Okay, let me try. Can't zoom in from here. I guess that's the max zoom from my side. So I'll just read what is here, then hope you can understand. So in the first two lessons, we learned how to build fully connected networks out of stack of dense layers. When first created, all the network's weights are set randomly. So this is what I was mentioning. So the weights are set at random. So the network doesn't know anything yet. So in this lesson, we are going to see how to train a neural network. So we are going to see how the neural network learns. So as with all machine learning tasks, we begin with a set of training data. So each example in the training data consists of some features together with an expected target. So training the network means adjusting its weights in such a way that it can transform the features into the target. Okay. So if we can successfully train a network to do that, so its weights must represent in some way the relationship between those features and the target as expressed in the training data. So we want the results that are there in the training data to be same in what we get when we do the testing. So in addition to the training data, we need two more things. So we need a loss function. So the loss function measures how good the network predictions are. And a loss function, you can think of it as an accuracy score. So this model will be checking the accuracy of its fitting each and every time it runs. Then we have an optimizer. So the optimizer tells the network how it can change its weight to minimize this loss function, okay, so that we can get a better accuracy. So let's go to the next slide. So let's discuss the loss function. So already we know how we can design our neural network, okay, but we haven't seen how we can tell our neural network to solve like a given problem that we present to it. So this is where the loss function comes in. So the loss function here measures like the distance that we have between the predicted and the actual values, okay. So it measures how far is our prediction from the actual value. So different problems call for different loss function. So for example, if we are dealing with regression tasks, we can use the mean absolute error as our loss function. Okay, and the mean absolute error measures the disparity, or maybe the difference between the actual and the absolute difference between the actual and the predicted. Yeah, so it gets the absolute difference between the actual and the predicted value. So if we were dealing with the classification task, we would use something like a sigmoid function, because remember when we were discussing logistic regression, I showed you the sigmoid curve. Okay, so I think this should be it. So we can use something like a sigmoid function when dealing with logistic regression. So anything that lies on this side is predicted as class 1, anything that lies on this other side is predicted as class 0, for example. So that's the main purpose of the loss function. So the loss function just measures the accuracy of your model. So how far are your predicted values from the true values? So yeah, so this is an example. So you can see we have this line of best fit, and here we have these lines here. So this dotted, this dots, these red points that you are seeing here in the plot are the actual values, and these blue lines that connect the points to the line of best fit are they are the difference between the actual and the predicted value. So what you do is you take the absolute difference of all of them and you will get your accuracy. So the lesser the number, the better. Then we have the optimizer. So what does the optimizer do? So as we have said, the optimizer helps the model in telling it how it can adjust its weights. So we've described the problem we want the network to solve, but now we need to say how to solve it. So this is the job of the optimizer. The optimizer is an algorithm that adjusts the weights to minimize the loss. So as I have mentioned, the lesser the loss, the better. So the higher the loss, the worse the model performance. So if we reduce this loss, or if we reduce this MAE value, then we will know that we are getting better results from our model. So virtually all of the optimization algorithms used in deep learning belong to a family called stochastic gradient descent. So they are iterative algorithms that train a network in steps. So one step of training goes like this. So you might have like 20 different trainings, and these are the steps that are done. So the model samples some training data and runs it through the network to make predictions. Then it measures the loss between the predicted and the true values. Then it adjusts the weights in a direction that makes the loss reduce. Okay, then it iterates this till we get a better value. So here you can see how it works. So with each iteration, you can see, for example, let's wait for this to start. So this is our line of best fit plot here. So first of all, it starts at a random point, but with each iteration that we make, you can see this line of best fits tries to cover like the majority of the points that we have in this data, so on the fitted line. And you can see in each run we have some random points flashing, so which means that we are using these random points to maybe fit our model. Then what happens to the loss? So with each training that we are doing, so which is called a mini batch. So a mini batch is whereby you are taking just some part of the data and doing a fit. So you can see that we are reducing the training loss, and we reduce the training loss till it gets close to 0. So from around 40 to down here where it's around 0, and you can see we have no further change. And here you can see as we are doing the trainings more and more, the weights tend to maybe get constant or maybe have a less or no change at all. So you can see from maybe batches 100, so batch 100 means fit number 100 or fit number 150. You can see the weight value starts to like flatten, which means that we've obtained the best weight that we could, and this is around 2, and we've also attained the best bias term value that we could get from this plot. So that's basically how it works. And how do you so I won't discuss these presentation because it's an explanation of what I've shown you here. So how do you implement this in your model? So it's quite simple. So once you've defined your model, so let's say this was our model, so we've created our model, we have our input layer, we have our hidden layers, and we have our output layers. So what we do next is we add this stochastic gradient descent part, and this is how we do it. So we type in, so this is our model, for example, so we've instantiated our model. So the next thing we do is we type in model.compile. Then after compiling, we add in our optimizer. So we have our optimizer, for example, we have the Adam optimizer. Then we add in the loss. So since this is a regression task, we can use the MAE activation function. So I think at the beginning of this notebook, I've added some reference materials to TensorFlow, so you can check this reference material and understand like some of the activation functions that we have. So everything is here. So you can check them there. So let's proceed, and basically that's all about the activation function, not the activation function but the optimizer and the loss function. So this is what we've explained in the presentation. So let's proceed on to the next part. So we've seen how we can create our model, but how do we run it? So the next thing we can check is overfitting and underfitting, but before that, this is how we run our model. So first of all, we create a variable called history. So after creating a variable called history, we say let our history be equal to model.fit. Then we pass in our x and our y value. Then, as I had mentioned earlier in this presentation, so this part where I'm saying the mini batches, so the mini batches represent the small sizes of data sets you are going to fit. Then the epochs here represents the number of times you are going to run this model. So here you can see mini batches represent the number of data points you are going to fit, and epochs represent the number of trainings you are going to do. So hope you've understood that. So that's how you basically fit your model. And here you can see we have 200 fits, and if we look at the loss curve from this fit here, so from the history we can extract, we can convert. We have something called history.history. So we have like the loss values stored in history.history. So if we convert this to a data frame and plot the loss, you can see what we get. So with each fit, the loss reduces, okay, and this is with a data set that is here. So I'll give you time to go through this notebook on a later time, but I'll also share the data set with you so that you can upload it and maybe use it. Okay, so that's the fitting part. So you can see how the loss changes with each fit that we have until we have no significant change. Yeah, so let's proceed on to the next part, which is overfitting and underfitting. So overfitting and underfitting in simple terms is when you are training your model, you might pass in less data points, which means that maybe you won't cover all the trends that are in this data. So that means you are underfitting your data, so your model won't know like all the trends that are in the data. Then overfitting means your model is too much confident and it's giving maybe high accuracy results which are not a representation of what is in the data. So let's look at this. So recall from the previous example, Keras will keep a history of the training and validation loss. So here I've only shown you the training loss, but we also have the validation loss. So the validation loss is whereby we have the test set, so over the epochs that it is training the model. So in this lesson we are going to cover how these learning curves can be used in guiding us in our model development. So we will be trying to see if there is an incidence of overfitting or underfitting. So how do you interpret these learning curves? So first of all, we have two things you need to know. So we have noise and we have signals. So what we need our model to learn the most is the signal and ignore the noise part. And if our model learns the noise part more, then we will be prone to the model overfitting. Okay, and if the model learns less of the signal part, then the model will be underfitting. So we need to have a balance between the two. So you might think about the information in the training data as being of two kinds. So we have the signal and the noise. The signal is the part that generalizes, the part that can help our model make predictions from the new data. The noise is the part that is only true of the training data. Okay, so this is the only part that maybe can be seen on the training data but cannot be replicated or when it comes to the test data. So the noise is all of the random fluctuations that come from the data in the real world. So for example, let's say we have a downtime in Safaricom. So we wouldn't consider that as a significant maybe event in helping us trying to like predict the hourly transactions of Safaricom, because we know this is a random event, so we will have never predicted a downtime in Safaricom transactions. Okay, so yeah, here you can see the noise is the part that is only true of the training data. The noise is all the random fluctuations that come from data in the real world, or all of the incidental non-informative patterns that can't actually help the model make predictions. The noise is the part that might look useful but it's not useful at all. So when we train a model, so we train it by choosing its weights or parameters that minimize the loss, as we've seen. Okay, so you might know, however, to accurately assess a model performance, we need to evaluate it on a new set of data. So that is the validation set or the test set. So we need to make sure that the performance that this model is giving on the training set is same to what we are having in the validation set. So when we train a model, we've been plotting the loss and the training set epoch by epoch. So this is the curve that we are talking of. So for every fit we are plotting the loss. Okay, but what we need to do is we need to add another plot, which is the so this is our training plot, so we need to add a second plot, which is the validation plot, and this is what we'll need. So for example, if we look at this plot, so if I was at this point, so I don't know if I'll be able to draw. So maybe if I was at this particular point here where this thing is, so I will say my model is underfitting because I haven't achieved the best loss yet. And when looking at the validation loss, so the best validation loss you could get is this point down here before the validation loss starts to rise, because what we want to achieve is the lowest loss value on the validation test, and we can ignore the training loss and at least look at the validation loss. So here you can see in our model, this is the training loss, so it's just reducing, but we haven't included the validation loss, and the validation loss will guide us as to how many epochs we need to run before saying our model is overfitting or underfitting. So let's look at what I've written here. Now the training loss will go down either when the model learns signal or when it learns noise. So when the model is learning a signal or a noise, it goes down, so it doesn't matter what it's learning. But the validation loss will go down only when the model learns signal. So in this case, this part that we have from here up to here where we have this line, so the model is learning signals, but from this part that we have here in the middle up to here, the model is just learning some noise. So when a model learns both signals, both curves go down, but when it learns a noise, a gap is created in the curves. So the size of the gap tells you how much noise the model has learned. So over here at the end, the model has learned a lot of unnecessary things that it shouldn't have. So yeah, this is a curve showing you how underfitting is and overfitting is. So underfitting is this case where you can see this is the fitted, this is the true curve, so the curve that we need. So this is our predicted line. So if we were to make predictions here, then this point, which is at 8, negative 1.5, and maybe 5, negative 1, 5, 1.5, 11, 2 would be wrongly predicted. So that's a representation of what underfitting looks like. Then this is a representation of what overfitting looks like. So we are trying to maybe make this model perfect, but we are forgetting that maybe this is the curve that we need. So ideally, we will create models that learn all of the signals and none of the noise. So this will practically never happen. So instead, we make a trade, so we can get the model to learn more signal at the cost of learning more noise, so long as the trade is in our favor. So the validation loss will continue to decrease after a certain point. However, the trade can turn against us. So the cost exceeds the benefit and the validation loss begins to rise. So what we need to do is we need to come up with a cutoff point whereby we say if the validation loss starts to rise, and we give like a threshold. So if we say like if the validation rises by 5 and it's no longer reducing, then we can stop our training there. And I guess that's what we are discussing here, so which is the capacity. So a model capacity refers to the size and complexity of the patterns it is able to learn. For neural networks, these will largely be determined by how many neurons it has and how they are connected together. So if it appears that your network is underfitting the data, you should try increasing its capacity. So what's increasing the model's capacity? So you can either do this by making it wider, so creating more units. So for example, this is a wider model. Wider, you can see this is a normal model, so model being equals to keras dot sequential. Then our input layer has 16 units, input units. Then to to make it wider, we increase the number of units. So we increase them from 16 to 32. So that's how we make it wider. And instead of making it wider, we can follow a second approach. We make it deeper. So we create even more hidden layers. So here you can see we have at least an additional hidden layer, and maybe that's how we solve the issue of underfitting and overfitting. Another thing we can do is we can work with early stopping. And early stopping, what it does is, as I have mentioned, so the model will do the training and fits, and it yes.
We are creating models on,
yes.
Let me say units.
Yes.
Right there on the deeper end or the deeper side.
Yeah.
Assuming you have 2 layers.
Yes.
And have let me say you have 16, 1.
Yeah.
And then assuming that we had 16 on the first one, we had 16, 1, then 32, 1. It was deeper than.
So this is wider, 16, not deeper.
Then you enter it, you have, it was wider.
Yeah, wider.
Okay, it was wider. Then you go to the more wide one.
This is the deeper one.
The deeper one. Oh, okay.
Yeah.
Then what we had? Okay, let me, before I say that, before I ask that, is there an instance that you're trying to create a deep one, but you end up overfitting?
Yeah, there could be cases. So what you need to do is you need to work with, so you need to combine this capacity part with early stopping, because early stopping is the only way you could be sure you are not overfitting your model. Yeah. So okay, so let me show you something. So this is a wider model. So a wider model will look like this. Okay. A minute, I show you.
Sorry, I couldn't guess it.
Okay, so when creating your models, so this is how a wider model will look like. So for example, these, why is my pen not working? Just a minute. Okay, so for example, let's say we have something like this. So this is our input. So a wider model will look like this, for example. So this is an example of a wider model. Maybe this is our output. So that's a wider model. Then a deep model will look like this. So a deep model has more hidden units, and a wider model has this part expanded. So instead of like you having 2 units here, you have 4 of them, but for a deeper one you can see it's extended. So that's the difference between deeper and wider. And now we have the early stopping part. So the early stopping part, here we monitor these validation loss. So if the validation loss starts to rise, then we stop the model from running. And how do we implement this? So this is the code that we use for implementing that part. So here we will have our early stopping being equal to early stopping. Then so already you know how you can implement the capacity part. So it's by changing how you instantiate your model. But adding early stopping, you have to create a new variable called early stopping. Then you need to define your minimum delta, and the minimum delta is the minimum amount of change to count as an improvement. Then patience. So patience is how many feet you should wait before stopping. Then restore best weight. So should your model maybe use the last fit that had the lowest loss? So those are the 3 things you need to define. So hope you understand them. So let's see how it's been implemented here. So here we've created our model. So here we are importing our model. So here you can see from keras, tensorflow.keras, import layers, then import callbacks. So callbacks is for early stopping. So here we will have early stopping being equals to callbacks dot early stopping. Then we've specified the minimum delta, so which we've said is the minimum amount of change to count as an improvement. Then patience, so how many feet should we wait before we could check for the change. Then restore best weight, should we restore to the last best loss that we had, or should we retain the current loss that we have? Then we go ahead and instantiate our model. Then we compile our model, adding the loss and the optimizer. Then when training the model, here you can see you pass in your X train, your Y train, and you pass in your validation data. So you pass in your validation data as a tuple, and you have to create this new variable. So this is one new thing we've added when doing the validation. Okay, then here you have to create these again callbacks, and for callbacks you have to equate this to this variable that you've created up here called early stopping. So you can see we've said that this model should do 500 trainings, but if we run the model, let's see how many trainings are done. So here you can see only 30 trainings, 30 out of 500 trainings are done. And this is how the validation and training loss look like. Yeah, so and if we maybe do the fit with all the 500 fits, let's see what we get. So this is with all the 500 fits, and this is what we get. So you can see the validation loss starts to rise and falls again, but you can see the training loss keeps on dropping. Instead of us, this is the second output with all the 500 fits. So you could, if you are using the training loss, you could say your model is performing better. But if you check up here, you can see this is the best result you could get. So let's look at the last thing that we can cover here, and that is dropout and batch normalization. So when fitting deep learning models, so there is a tendency of one layer learning bad habits from a previous layer. So what should we do to like eliminate this? So there is more to the world of deep learning than just dense layers. There are dozens of kinds of layers you might add to a model. Some are like dense layers and define connection between neurons, and others can do pre-processing and transformations of other sort. So in this lesson, we'll learn about two kinds of spatial layers. So not containing any neurons themselves, but add some functionality that can sometimes benefit a model in various ways. So the first one is the dropout. So the first of these is the dropout layer, which can help correct overfitting, but it's not a must you use the dropout layer. Okay, so the idea behind dropout is to break the conspiracies that exist between connected neurons. So if we go up here, so in the last lesson we talked about how overfitting is caused by the neural network learning spurious patterns in the training data, so learning noises from the data. So to recognize these noise patterns that a network will often rely on so the network will rely on a specific combination of weights, a kind of conspiracy of weights. So the model most likely depends on the same weights, which should not be the case each and every time. So being specific, they tend to be fragile. So if you remove one of the neurons that we have in the data set, so these trends that have been learned tend to not exist anymore. So that's the idea behind dropout layers. So here you can see, if we add, for example, a 50% dropout layer, and let me draw this. So if we draw our model, so for example, this will be our feet. So I can say that that's our first input, 1, 2, 3, 4. One, 2, 3, then 1. So if we are doing a feet, then this maybe will be our first feet. Okay, then we can have that. Okay, so we can have that. So for the first part, which is the dropout layer, yes.
What about the first?
So I'm drawing the first unit to show you how it works.
On the first one, the first layer. On the first one, the first one is the first layer.
Okay, this one here.
On the one you have drawn, yes, the one that you have drawn.
Okay, so you can ignore these ones here. Okay, let me redo this, then I can explain it better. So let's have a blank template here. So this is our X, right? Then here we have our first layer with, let's say, 4 inputs. So it gets input from our X. Then here we have our second layer, for example, which has 2 units. So we can have something like that. So when adding dropout layers, so we can say like these and these can go there. So the outputs from these 2 units can go there, and then the outputs from this can go there, so that anything that was learned on these 2 units won't be the same thing that these 2 units learned. So what this means is that the model, so for this part that we have here, the model won't be looking at what has been learned here on the orange part and maybe try move on from that. So it will have two separate inputs. So here we will have maybe output y, then here we will have output y1. Then the model can come and combine this to come up with output y0, and output y0 will be a combination of trends that have been learned on this unit and trends that have been learned on this unit. So trends that have been learned on this unit are different from the ones that have been learned down here, and basically that's how dropout layers help. So let's look at this. So you could also think about dropout layers as creating a kind of ensemble of networks. Yeah, actually this is, so from this explanation here I can maybe explain it better to you guys. So remember, when we were creating a random forest model, this is what we had. So what the random forest did is, for example, it would follow these, it will follow this path here and ignore everything that is here. Then it will go ahead and create a second model, and for the second model it would follow, maybe let's say, this path and ignore everything that is on the left side. Then it will combine all these model and come up with one average score. So basically that's what the dropout layer does. So it's like creating a random forest model where each unit here learns a different pattern from the data, and then the patterns are combined to come up with an average output, which should be better than when you fit the whole model as a whole. Yeah, so that's all about the dropout layers. And the last thing is the, so how do you add the dropout layers? So after you've defined your, after you've created your layer, so what you do is you type in just layers.dropout. Then here you specify the percentage you want to drop out. So mostly you can use 30 to 50%. So here we are using 0.3%. Then the last thing you can add is the batch normalization. So I will explain this in simple terms. So batch normalization is just the scaling of your data set. So you can think of it as standard scaler or min max scaler. So this means that for each so for each and every neuron that we have in here, so the data, let's say the data is scaled here. So in here, if we do not add the batch normalization, the data is not scaled. Okay, so this data is not scaled. So what batch normalization does is it scales this data that is here. Then this data goes to be an input here. So this data is not scaled. So if we add the batch normalization part, then it scales this part again, and so on and so on. And how do we add it? So after adding the dropout layer, we add the layers.batch normalization. So here you can see we have our input layer, we have the dropout rate, and we have the batch normalization. And basically that's how you create your model. And finally we have the final model that we want. So from that I can summarize the deep learning part, and I think the remaining part is the classification part. So for classification part, I'll leave that to you to research more, because the only thing that you change on classification part is this. So here you can see when we are fitting the model, we say model.compile, then we say the loss should be equals to MAE. So when dealing with classification, we say model.compile. Then for the loss we use a different loss, so the binary cross entropy, and we add something else called a metric, and that is the binary accuracy. So that's the only thing you need to change. And you also need to know what kind of activation function you add to the last activation function. So I'll leave that to you. So yeah, from here I can summarize everything that we've learned. So first of all, it's creation of our model. So how do we create our model? So we have our model being equals to keras.sequential. We instantiate our input layer, and the input layer has the number of units, has the activation function, and has the input shape. And the input shape represents the number of features we have in the data set. Then the next thing we do is we add the dropout layers. So how many units should be used for as input for the next hidden layer. Then we normalize our data set using the batch normalization. Then we proceed on and create our hidden layers. Then lastly, we create our output layer, and the output layer has only a single unit. And the output layer for regression tasks has no activation function, but for classification tasks, the output layer has an activation function, and the activation function for the classification task should be equals to sigmoid. So if you go through these notes, you'll get to see that. Then after creating your model, what next do you do? So you compile your model, adding the optimizer and the loss function. And after adding your optimizer and the loss function, what else do you need to add? So you need to add your early stopping, and this is the part where you add the early stopping. So you define the minimum delta, the number of fits, and if you want to restore your model to the last best value, then you go ahead and fit your model and you store your results in history. Then you are going to use this same code that is over here to plot your validation and training loss. And that brings us to the end of deep learning. So I haven't covered deep learning in detail because if from the start of this learning we mentioned that 90% of machine learning models are never implemented in the real world. So what's the probability of you implementing a deep learning model? So your chances of you working with a deep learning model are reduced, not unless you are working at big companies like Tesla, which are more reliant on such kind of models. Yeah, so that brings us to the end of the deep learning unit. So maybe we can have a brief discussion. If you want to, I can answer a few questions from you, then we can call it a day.
Listen,
Yes.
are there instances where we have more than one output
Output no. You can never have an instance where you have more than one output unit. So the output layer will always have a single unit. You can't have multiple units. So that's what defines an output layer. So it's a single unit.
Okay.
Yeah. Any other question? Anyone else with a question? So I guess I'll have to get the data set that I've been using for this project. So let me try get it. So I can stop the recording and